Down. Is correct?
Correct.
Thanks. Thank you. Talking about fundamentals of MOFs, mechanics and structure mechanical property relationships. Please.
Thank you, Andre, for the introduction. So good morning, everyone, and thanks to the organizers for the fantastic conference dinner, workshop dinner, I should say, last night. So I'm glad everybody returned this morning on time. So let's get on with business. So I'm gonna talk about the basics, if you like, of the mechanical behavior of metal organic frameworks, or abbreviated as MOF, morphed materials. I think some of you are familiar with this, and we have seen a few examples yesterday. So particularly focusing on these aspects, which are emerging, or we're starting to understand more now than before, and isotropy in terms of their mechanical behavior, the use of near-field probes. These are new diagnostic tools that are available that I'm just going to share with you, and also more understanding about their defects and fracture behavior, what happens beyond elasticity. So these are the outlines. Hopefully we'll be able to cover this morning. Introduction of morph materials. We're going to talk about morph mechanics from the perspective of elastic behavior to plasticity and beyond. Then nanoanalytics. These are things like near-field spectroscopy, also known as nanospectroscopy, short nano-FTIR, and tip-force microscopy. So very fine-scale probes that you can do under atomic force microscopy. Okay. Now, quick intro slide on metal organic frameworks. Particularly, I'm going to focus on zeolitic imidazolate frameworks, or ZIF. ZIF-8 is a topical exemplar, as you can see, for liquid intrusion applications. But there are other ZIF materials that are potentially interesting as well that I'm going to bring up. Okay, so the general idea is you do some self-assembly of the building blocks. So this consists of metal nodes and organic linkers. They build secondary building units, SBUs, cages, which could be like these 4-member rings, 6-member ring, etc. Self-assembled into certain topology. In this instance, a soda-like cage, which is the one of ZIF-8, but there are very many other topologies out there, and they self-assemble to form crystals, which are extended 3D frameworks. Okay, so what is of interest to this community is that we got the internal core, which can be evacuated and then utilized, right, to encapsulate some gas molecules, for example, liquids, and other species, if you like. Now, morph materials, in terms of engineering, you can envisage that you can shape them potentially into these different morphologies or architectures. Single crystals are great for basic science research to find out their fundamental behavior. But for applications, we usually need to further mold them into, say, monoliths or fibers. In this example, we achieved them by a method called electrospinning. But this is in combination with a polymer as a support. You can also form thin films or membranes, which could be functional. So those are a few exemplars. Now, in my group, we have been working for a few years now on luminescent morphs. So the framework itself is benign, which is non-luminescent. But when we capture or confine a luminescent gas, which is like a fluorophore, they become luminescent and could be used for all kinds of applications like this, which we summarized in the recent review. So just to point out a few examples, electroluminescence is a possibility, so we show that this could be achieved. Sensing of volatile organics, so vapor sensing detection, so using fluorescence method. Temperature sensing, reversible. Pressure sensing, I think extremely exciting. So mechano sensing of stress, strain, and some coupled interactions. Okay, And more recently, we've been doing also some triboelectric harvesting using such systems. And indeed, the tunability that is provided to us through the very varied architecture of MOFs is advantageous. So always one of the limitations of MOFs is that the long-term stability is not as great compared to inorganic materials. So, and just some revision on basic ideas about mechanical behavior material. This is indeed very basic undergraduate material, but hopefully we can pick this up and move on with more complex ideas, right? So let me just summarize. Well, basically we put this in our recent book. You can grab this from the RSC website. First chapter is absolutely free, no watermark, anything you can just start. If you have a stress strain curve, so you have a classical solid, which is isotropic. If you pull it uniaxially, stretch it, that is, what you get is you have an elastic response from this origin, right? Up to a point where it's called the yield point, when things start to become non-linear. Or for brittle solids, very often they just simply break here, so you don't go further. However, if you do under compression, usually we can get a bit more. So even for brittle solids like MOFs, I will show you later in our recent work, we can squash it and you can get some plastic-like flow, I would say, yeah? Not entirely dislocation driven, but they look like plasticity, okay? And you can go to a certain maximum stress or something beyond when you break the structure by fracture. Okay, so you can do some unloading, etc., cycling testing. So you have some elastic regime and, broadly speaking, some plastic deformation. So under the uniaxial loading, if it were isotropic, so the Young's modulus is defined by simply the applied stress, sigma divided by your axial strain, which is in this direction, I. Poisson's ratio, of course, is the ratio. Again, this only applies in uniaxial loading. Don't get confused. But simply, as I sketch out here, so this will be the strain in the transverse direction, so this way, and divided by the strain in the axial direction where you actually apply the stress. So that ratio will give you the Poisson's ratio. So this is still classical solid. For porous materials and other unconventional solids, you can get negative Poisson's ratio and other weird stuff. So that we can touch on later. Now, shear is extremely important. I think I've worked on this for a while now, and for porous materials, which are really open framework, we suspect the angular distortion. This is one of the things that can really break your framework. So either by torsion or just by, a distortion like that, simply represented here by the shear stress divided by the shear strain. And of course, for liquid penetration tests, all these, if they were hydrostatic in nature, then about modulus would be relevant. Or the inverse of this property, which is called the compressibility. Anyway, so let's move on. So this is very recently published, although the work was done a while back, in fact, in ETH Zurich. So I have a collaborator there who now left. But when we did it, we thought this was quite difficult. Indeed, it was difficult. And it was even more difficult to write out. Anyway, it just came out this year. So what we did is we have a single crystal of this MOF material. This is called the HCAS1, I think very topical. We use it because we can grow sizable crystal, which we mounted here, so it's 1 centimeter or less in size. And this is under the, this is a focused ion beam system, FIB. So you have SEM as well as a gallium ion beam. So the gallium ion beam is going to machine all these trenches and make pillars out of it. So we are looking at 2 different crystal orientation, 111 and 100, for the obvious reasons that they are strongly anisotropic. So you see that the projection down this way and down that way are completely different in terms of the connectivity and so on. HCAS1 was extremely porous system. So one of the fear was material damage. So we see all this sort of cracking, but subsequent testing revealed that actually, these pillars are not too much affected by this macroscopic or microscopic damage. So the aspect ratio was retained like this, so 3:1, so that we can prevent buckling. So anyway, the movie, I think it played and stopped. Go back. Right. Yeah, so we are squashing this, and you see that. So the length is the same for both samples. It's just the viewing angle gives you the impression this guy is taller than that. It's actually not. There's the 100 direction, shows some kind of strange buckling. This could be due to cracking as well at the root, but we cannot visualize that. But it's clearly different from the 111. Again, just to remind you, these are small, what we call micro pillars, because the diameter is only 5 micrometers. Now, the behaviors are quite surprising. So we find that you have this elastic response, but beyond that, we got what looks like plastic flow. So this is under compression, not under very confined conditions, because these pillars, they are freestanding, well, supported at the root, that is. The yield stresses, you see, so we try to extract that from the deviation point, and the yield points are quite different between the two. So the source of isotropy could be associated with this underlying framework architecture. Not to scale, these are just cartoons, just to show that the connectivities are extremely different down the 111, which are significantly higher in the yield strength compared to the 100. Anyway, so that's as far as we've gone. Now, it would be useful to construct a map like this, summarizing where the behavior of metal organic framework materials in relation to other conventional engineering solids, if you like, and in relation to zeolites, right, which is an important field on its own right. So zeolites, here we are plotting the Young's modulus or elastic modulus, more broadly speaking, against hardness. So hardness, the definition is just you have a maximum stress, you divide it by the contact area. So that is the hardness. It is a measure of the plastic response of the material. So you can quickly see that for zeolites, which are inorganic porous solids, so the stiffnesses are in the range of 10 to 100 gigapascals, the hardness 1 to 10 gigapascals. Okay. So in the inorganic or ceramics zone, if you like, MOFs and ZIFs, they are at least an order of magnitude lower. So we are looking at things which are 1 to 10 gigapascals in terms of the modulus, and the hardness, again, hundreds of megapascals to about 1 gigapascal. So, well, the distinction is not clear if you just look at the topology. So they could have the same topology. However, if you look at the chemistry, they're extremely different. These are silicon, oxygen, silicon joints or linkages, which are relatively more rigid, I say, whereas these guys are more flexible when you have the organic bridging linker and you have the metal nodes. So to understand this a bit better, we have done single crystal works. Anyway, the next slide is just to show that there is an update to this map if you're interested. So this was published way back when I was working in Cambridge, 2011. So whilst preparing this new book, so we were looking at the latest data available. There was some expansion to this area, which are now incorporated. And also there are some intermediate regions that are now expanded. These encompass materials like hybrid organic, inorganic perovskites, which might be of interest to some of you for solar applications and such. Anyway, if you're interested, you can look at the reference now. Okay, so to begin, let's look more about nano indentation, because this is indeed the technique that has been used a great deal to obtain all these behaviors that I've put together here. So in nano indentation testing, we need a flat, good surface to work with. And what you do is you have a very hard probe, typically diamond or other hard solids, which are well defined in its geometry. Then by squeezing or penetrating the surface, we track the load change as a function of penetration depth. So it's quite parabolic for a conical or Berkowitz type indenter, and then you do the unloading. So for modern instrumented indenter, usually during the loading is doing some small oscillations, and you can see there are mini unloadings happening here. Traditionally, so you get the stiffness from this unloading curve, dPdH. However, for modern machines, whilst you're indenting, you're also getting the stiffness measurements, which is nice because that tells you how the stiffness or hardness is changing as a function of surface depth. Right, so here are the some plots showing that depending on the probe that you use, the behavior that you can probe could be significantly different. So for a spherical indenter, you see they are predominantly elastic, so the very little hysteresis, you would like to look at it that way, or plasticity. Whereas for Berkowitz, it's more open, so there's more inelastic behavior. And there's some kind of yield point as well for this example. So these are study to look at different topologies. So not just ZIF8, but very dense framework like ZIF-ZNI, which has a small accessible volume, 10% or so, ZIF4, 7, 8, and the bigger ones like ZIF20. So as you can see here, so the modulus are changing with depth. Some are more sensitive to depth, others are not. So the take-home message is when we plot the elastic modulus as a function of density, there's some scaling going on here as a function of the framework packing or density, and inverse relationship to the openness or the porosity of the framework, which is not unexpected, but it's good to establish. Now, to study anisotropy more closely, because in nano indentation, you're actually probing the solid in three-dimensional space. So the response is more average up than unidirectional or uniaxial in that sense. So one of the studies that I did, this was way back. This reference is actually wrong. So this one was a work from 2011 earlier. So it was using laser Brigalow scattering. So the single crystal, the sample is just down there where my red dot is. The thickness is only 100 micrometers or less. So the idea is to extract these elastic constants from a slice of this crystal, and being cubic, there are 3 independent elastic constants. So C11, 12 for axial shear coupling, and shear C44. Axial transverse coupling, I should have said. Anyway, what important here is that we have an isotropy in the elastic response, although not very strong, but you can clearly see that if it were isotropic, it would have been the sphere, but it's not. And for this cage sodalite, so we can then establish in terms of the directions where the maximum and the minimum and the intermediate stiffnesses are. And then in conjunction with theoretical calculations, so these were done using Crystal 09 code, DFT calculations, density functional theory. These were in collaboration with University of Toronto. So we calculated these elastic constants, which in good agreement with these experimental numbers, which we can then use to simulate how the angles and the distances of the bonds are changing. So basically we are monitoring in this tetrahedron, so the distance between the zinc and nitrogen. So of course under uniaxial tension, simulation, they will be scaling linearly. And the angles, nitrogen, zinc, nitrogen, either they are opening up or they are collapsing. Well, they have to be that way so that you have some compatibility in the structure. So we don't break it. So these are all elastic studies, right? Further to that, as I alluded to earlier, the shear is extremely interesting to look at. And you can see that the values, these are the measured values. They are small, typically 1 gigapascal or so. This turns out to be true across all the ZIF type or MOF type materials, unless they are very dense solids. They are typically in that low range of a gigapascal or so. And the Brigalow scattering in conjunction with DFT help us reveal the maximum and the minimum in terms of shear modulus. So what I just want to show here is just the anisotropy that should be appreciated. Okay, let's move on. Now, moving from elastic behavior, so the next step was to think about maybe some dynamics, and this could be in the form of terahertz vibrations. And we have looked at that using synchrotron far IR. So this, you could call them terahertz spectroscopy, and using elastic neutron scattering. So this is INS. So these are looking at low energy region to study the collective modes, as I've illustrated here. So wave numbers I have got here, so you can see that less than 10 terahertz. So there are modes that are common to different ZIF material 4, 7, and 8. Okay, and you can see that yes, for the higher energy band, like here, this could be associated with the linker modes. So the DFTs help us to understand a bit more the origin of these vibrational bands at low energies. So these could be associated with soft modes, shearing, and in particular these ones which we call the gate opening, particularly relevant when you try to intrude stuff through the passages. The windows, when they are closed, are narrow, but there are soft modes or this gate opening vibration that could be triggered. Now that brings us to some liquid intrusion study, which Yuting already explained yesterday, and with some simulations aided by Swen's work. So especially I want to draw your attention to ZIF 71. ZIF 8 has been done a great deal by the community here, but 71 I think is pretty promising. It's not difficult to synthesize, so that's always important for engineering use. And the material stability is quite good. Anyway, so it's up there. There are other candidates, of course, but I suspect the synthesis is not so straightforward. Anyway, so ZIF 71, the structure is like this. So I think one of the attractive points is the largest cavity diameter. So this is about 2 nanometer, yeah, to begin with. The linker is this DCIM, dichloroimidazole. It is quite painful to simulate because it's a big structure. So I'll get to that later. But experimentally, really exciting. And these were the dynamic, impact intrusion experiments that Yuting showed us yesterday. So the black curve, I think, inside is quite narrow, or blue curve, in fact, and at higher strain rate. So this was 10 to the minus 5, a quasi-static, 10 to minus 2. You can see that the intrusion pressure went up and the extrusion pressure went down. So energy absorbed has increased, and more significantly even at 20 per second. So pretty impressive behavior. I think highly reversible as well. So in terms of the energy absorbed as a function of strain rate, you see that it shoots up very quickly at a strain rate of just 10 or 100. This already exceeded the capacity of our system, so we cannot measure beyond. Whereas systems like I think ZIF 8 is doing much later, up to 1,000 per second is required to get that kind of performance. So we think that was exciting. So there was a follow-up study, therefore, which we published in 2022, just to look at all these soft modes that are potentially the enabling mechanisms to such behavior. So the far IR again is being used, the terahertz modes. So these are low energy, so 20 terahertz and lower, particularly at 10 terahertz, you see the tetrahedral vibrations here, which then we try to understand a bit more from the DFT work. Extremely painful to simulate. The student took 2 years, I think, to solve this. Yeah, there are 800 atoms when you break the symmetry. Now, from the experiments, so these are experiments down here. So all these highlighted low energy bands that are associated with the collective vibrations. One of which is to do with gate opening. So that was important. So now let's quickly move on to look at gas atmorph systems. So various gas could be encapsulated. This could be luminescent gas like rhodamine, fluorescein, or drug molecules if you like. But one of the questions is whether it's in or out. When we were doing this, well, in or out, we were at the Brexit stage, so we thought that was really relevant, but it's also relevant for gas morph systems. And indeed it is. So to try to probe whether your molecule is actually immobilized on the surface or is actually inside. So it depends on the application, both could be useful. Anyway, so what we're utilizing is nano FTIR. So this is a scanning near field optical microscope, particularly the scattering type. So you have a femtosecond laser coming in, and it's an AFM probe which is stepping, but it's never really hitting the surface, just near field interactions. Okay? So it causes some polarization under this volume, and the probing depth is about 20 nanometers. So we are looking under the surface. So there are vibrational modes like this, which can be picked up point by point at 20 nanometer resolution. And this is a nano FTIR spectra compared to your typical powder spectra with the ATR measurement. So the powder spectra looks very uniform because this is average, whereas this is from a single crystal, which is 100 nanometer in size, and the DFT at the bottom. Right, so I want to show you in this example, this is the extreme, where if your material has a mixed phases after your synthesis, so you could have your gas molecules crystallize out like this. Morphology is quite different, which is easy to see. So you put your probe there, you quickly see, oh, this is actually not my morph at all. This could be a gas. In this example, the luminescent rhodamine B. Okay, but as a ground up material, when it's averaged out, it's really hard to see. So point by point, we can really tell where the gas materials are, or whether they are truly encapsulated or just on the outside. For this example, when we probe at position 3, so the spectra looks like this. So we are really not looking for superposition here. So we are looking at changes that are due to host gas interactions. In this example, there are shifting of certain bands that are due to host gas interactions between the framework and the luminescent gas. And also changes in the ratio of the intensity of the peaks. And this again can be associated with that. And this is on a single crystal. So you can think of further doing nano imaging. Again, so we have done mapping. The red region here, this is the band associated with ZIF-A, and here these are the rhodamine B before we wash it. So there are species attached to the surface. After we wash it thoroughly, so it is still luminescence under fluorescence spectrometer, but when we do nano FTIR, the rhodamine B is no longer there. So there are surface species that could be removed. They could leach out, of course, that's not an impossibility. Now, I think I have to quickly screen through this. This is about making bulk materials and using what is a method called tip force microscopy. We can really look at the surface features. So what is of interest here? We've done nano indentation, and in combination with nano FTIR, we can then go in. So this is only 2 microns in size, so these few microns. So point by point, you can measure the change in the chemical structure from the vibrational bands. So want to draw your attention to this region, 1300. So this is associated with the region which is down here. So this can be achieved only when you have an indenter, which is a cube corner. So the stress is really high at the tip. So you see some hot spots here, which were not present by using a more blunt Berkovich tip. So we think that has to do with some defects, because we have done a control experiment where we grow the crystal 1 minute, 5 minutes, and 60 minutes. Multifaceted, but they are all ZIF-A. And then by DFT simulations, if you pretend there is a missing link, missing metal node or missing linker, so we see these anomalous bands. So these anomalous bands match up with what we saw from the nano FTIR. So there are indications that they are associated with some breakage of bonds. And finally, cracking, I have to really wrap up. 2 minutes, thank you. So we produce a map trying to show how the fracture toughness is changes with modulus. This is associated with maps inspired by Ashby. You see that no materials actually exceeded, so they're impossible to reach. Lower limit, you see some of the hybrids indeed are sitting there, not grain news, but a lot of morphs and monoliths, they are in sort of this region. Okay, so one way to measure this by indentation cracking, as I have shown here. This is from a literature published by another group. Or you can do some kind of experiment from micropillar splitting. So As you can see, due to anisotropy, there's some effects in the fracture, and simple relations that were proven to work for other conventional solids were adopted. But we think this is not working that great, I think, at the moment. Anyhow, we get an estimate. They are not significantly different, although the curves look very different because of this dependence on the ratio E over H. They are very different for the anisotropic solids. I mean, anyway, the threefold symmetry, I think, is causing an issue here to really probe anisotropy. Anyway, in terms of summary, so I think morph mechanics, so you can think of it in quasi-static way or more dynamic in nature. They are quite revealing. Nano FDR, hopefully I've shown that this could be a useful tool, and in combination of theoretical calculations, usually very helpful when you're dealing with very complex systems. So thank you very much for your attention, and I'm happy to take any questions.
Informative questions, please.
Thank you for a very interesting talk. I was wondering, you mentioned that there was a very complicated calculation which took your student.
Yes.
What was the difficult?
I think just the size of the problem. So it was 800 atoms, and we were doing the hybrid functional P3-lib, and yeah, it's a. We use I remember it took a long time to set it up and even longer to run. So partly I think the code wasn't up to it, and we were using the crystal code developed at Torino, and finally we managed. But we were then trying to solve the elastic constants, even that was not solved yet at the moment. Yeah, but the vibrations were done.
Thank you.
In your experiments, when you showed nano-FTIR and near field IFM, so you mentioned there are temperature increase when you are putting, right, or I misunderstood?
We don't monitor the temperature rise. I suspect it will be minimal or negligible. It will be negligible because it's just near field interaction. It's not really in contact as such. There's no mechanical interaction, I think. Yeah.
Yes, please.
Thank you for the presentation. There's a question about the mechanical properties of the material. That when you make the nano indentation, do you have to provide a Poisson ratio for your the elastic modulus of your? When you make nano indentation, you need to take in advance the Poisson ratio of your
Positions.
Yeah, the Poisson ratio, because you need to calculate it with that one, the elastic modulus, no? And how do you calculate it or obtain the Poisson ratio?
The position ratio?
No, the Poisson ratio.
Poisson ratio, yes. So, sorry. Either you assume the value, which is typical, yeah, or you can neglect that completely, and we quote a number which is called the indentation modulus.
I was asking because
yes, it's always a problem.
Yes,
and it becomes more weird because from DFT, some framework in certain directions are negative Poisson's ratio, which will break down when we try to use the classical formula. So,
thank you.
Yes, the last question, please.
The last part, which is the one and if in the case of Zeebrugge completion, what
for the unit, we were trying to look at, you can try to get Young's modulus, assuming certain things, or more interestingly is the flow beyond yielding. So after the elastic part, so we were interested to see whether it's going to shatter completely. So very brittle, and we were surprised to see there's some plastic, like not associated with dislocations, I can guarantee, because the structure is not metal-like. They're not close back.
Well, No further questions. Let's thank again. Well, we have a small change in the program. One presentation has been advanced, so it will be delivered now by Paolo Guglielmi. The title is Drug Loaded Metal Organic Frameworks Conjugated with Monoclonal Antibodies for Anti-Tumoral Purposes. Sounds very interesting.
Thank you very much.
Go ahead.
Thank you, thank you, the organizing committee, for this opportunity to talk about this outside and our experience in the use of metal organic frameworks as system for drug delivery started a few years ago when we tried to develop a composite system composed by magnetic nanoparticle included inside the metal organic framework structure. We choose two materials to reach this goal that were metal organic framework among the metal organic frameworks MIL 100, and for magnetic nanoparticles we selected iron oxide and in particular gamma magnetite. We are interested in the metal organic frameworks among the other properties that they possess also for the high porosity. The pores that contains these materials can be sites for location and loading of drugs. So we selected MIL 100, that is a microporous system with a super tetrahedric structure and with gauges of 29 and 25 angstrom of diameter. And we performed the synthesis of this material through a mechanochemical approach. So we use this Teflon coated jar, zirconium oxide bolts, and we perform three types of grinding: neat grinding, liquid assisted grinding, and neat grinding in the presence of dispersing agents. In particular, we employed these three kinds of synthesis, three types of approach. For the synthesis of MIL 100, the liquid assisted grinding. For the synthesis of the iron oxide nanoparticles, we employed the neat grinding in the presence of dispersing agent with the aim to limit the growth of the particle, to reduce the particle dimension. And for the synthesis of the composite, we followed a procedure with two steps. The first step, based on superficial surface derivatization of the magnetic nanoparticles that were decorated with tumesic acid through neat grinding. This step was fundamental to address the growth of metal organic frameworks around the magnetic nanoparticles. And in the second step, inside the jar, we inserted also the ferric chloride and performed the synthesis of the material. We characterize all three this material with different characterization techniques, in particular with X-ray diffraction. As you can see, the material MIL 100 exhibited a good crystallinity, and also the peaks were in line with reported data. IR analysis also confirmed the nature of the material, and the thermogravimetric analysis give us information about the composition of the system, giving us the opportunity to see the organic and metallic part that are included in this system. However, one of the main results that interested us was the specific superficial area that are the pores that are accessible to nitrogen in these experiments, and we found a superficial area of 1,100 that is quite high, and so we try to use this material for drug loading. Along with this, we also characterize magnetic nanoparticles. Also in this case, we performed X-ray diffraction analysis to check the nature and the crystallinity of the material. And along with this characterization, we performed STEM analysis to observe the dimension of nanoparticles. And magnetic studies were done to understand the magnetic behavior of these materials. And we interestingly found a super paramagnetic behavior of this material. That is a high susceptibility to external electric field without hysteresis cycle. So when the external magnetic field is removed, the nanoparticle lost their magnetization. This is important for biomedical application and for this kind of use. So as a last part of this project, we performed the characterization of the composite material coming from the merging, the fusion of the two systems, and also in this case in X-ray diffraction analysis we found the peaks of both the two crystal structure, and in the thermogravimetric analysis, we observed an increasing percentage of metallic parts due to the presence of the iron oxide magnetic nanoparticles. And on the other side, we observed a reduced superficial area due to the reduced amount of the MOF, because magnetic nanoparticles are a non-porous system, and also quite reduction of magnetization of the system because part of the material that has been analyzed in this kind of experiment is the paramagnetic MOF. And as a final part of this project, we performed degradation studies in simulated physiological condition in phosphate buffer, and we observed a complete degradation of MIL-100 in 25 days. And in the same days, we also observed the shell of MOF of the composite system, observed the same degradation in the same time for the shell of MOF included in this system. And we try to load this drug. This is an anti-tumoral drug used for many kinds of drug. However, these drugs have an important toxicity that is cardiotoxicity. So the inclusion of this drug inside the drug delivery system could limit this kind of problem. And we perform a drug loading after the synthesis of this material. However, we obtain low loading of drug with only 6.5% for the MIL-100 and 2.2% for the composite. On the basis of the percentage of MOF present on the composite system, we pulled that 4.7% of drug loading. So we search for the reason why we didn't have this kind of loading, and we found in the pore distribution the reason of this data. In particular, we observed the presence of a series of mesoporous cage in the MIL100 that are not present in the composite system, just justifying these results. Moreover, we performed the release study of the drug. We observed only a partial release of the drug by this system. In particular, for the composites, we released only the 20% of the loaded drug. Maybe there was an interaction between doxorubicin and magnetic nanoparticles. And then another aspect that I would stress is this first part of the release, because as you can see, in a very short time, there is the release of a high amount of drug. It's not so high, but it's quite important, and it is often named as burst effect. And in general, we would avoid this kind of behavior. We try to relate this behavior with different kinetic model, but none of this was effective to justify this behavior, that it's a complex behavior probably due to a mixture of erosion and diffusion phenomena. So, in conclusion, we developed this system. We try to load this system with drug. However, from my point of view, there are two issues that need to be solved. The first, how to increase doxorubicin loading, because 6.5 or 10% of drug loading is quite low. So, the first issue that I want to challenge is how to increase doxorubicin loading. We try to solve this problem by choosing two systems, not one. The first is still the MIL100 that has been reported to be able to load up to 18% of doxorubicin. And the second system that we chose was the MIL101, that with regards to MIL100 is a mesoporous system. To face this problem, we try another approach, another synthetic approach, that is the in situ encapsulation of doxorubicin. And through the addition of doxorubicin during the synthesis. So we try to obtain the material with doxorubicin inside the system, and leading to the construction of this material and incorporating this drug inside the structure. This should lead to drug loading, an increasing drug loading, and a reduction of burst effect. So we search in the literature data for a useful synthetic approach. We found some synthetic approach. The first of Wang and colleagues that try to separate nucleation from crystal growth to avoid excessive growth of the crystal. And the second approach that we choose was the microwave assisted synthesis that is known to favorit nucleation towards growth of the crystal. So for the first approach, we used this kind of system. So we created two different solutions of the organic linker and the inorganic joint. And through a peristaltic pump, we added these solutions inside the reactor to obtain always a condition of supersaturation leading to a fast nucleation without growth of the crystal. We performed this kind of synthesis for 1100 and 1101. We obtained good results with crystal structure. To be perfectly honest, this is a semi-crystal structure. There is a small amount of amorphous part, and also thermogravimetric analysis confirmed the nature of the material. Similar was observed for 1101. For the microwave assisted synthesis, we employed this procedure. We performed the synthesis at 130 degrees for 6 minutes. We obtained interesting results for 1100. However, in this case, for 1101, we tried different procedures, but none of these procedures led to the synthesis of this material. We were not able to obtain 1101 through microwaves assisted synthesis. So we obtained low ions. So we did not choose this route for the synthesis of 1101. And we started the synthesis of the material with in situ encapsulation of doxorubicin. Before this synthesis, I thought, why no one tried to do in situ encapsulation of the doxorubicin? Then I started the synthesis. And when the first amount of ferric chloride dropped out in the system, I saw this. This darkening. So I thought, this is the reason why. This is the reason why up to date no one tried this route. I cry inside and also outside. But I performed the synthesis. I performed the synthesis up to the complete addition of the two reagents. And interestingly, this darkening is due only to the complex constitution of a complex between doxorubicin and iron. Because after synthesis, we obtain the system, we obtain the crystal structure of 1100, and also thermogravimetric analysis confirmed this structure and confirmed also an higher percentage of organic moiety inside this part due to the presence of doxorubicin. And we evaluated as a preliminary data a 42% of doxo loading. On the other hand, we also try to understand that the dimension and of the system, and to be honest, it's quite high, being around 400 nanometers. That for biomedical application is not so good, but as a first attempt, it should be acceptable. So we try the synthesis of the same system with microwave assisted synthesis. We also in this case obtain good results from the structural point of view, but in this case the drug loading was lower with only 20% of the drug loaded. And we also obtained a bigger dimension of the particle, of the nanoparticle, and also a non-normal distribution of the dimension. So this kind of synthesis, maybe it's not the good choice for us. So we tried the first approach of Wang and colleagues also for the other MOF, that is the 1101. Also in this case, we observed a good crystallinity, better than the system without doxorubicin. And also in this case, we observed a 28.5% of drug loading. That is a good result. And also in this case, however, we observed a big dimension of the particle and a non-optimal distribution of the particle size. So in the light of the results, we choose the system of MIL100 as the system to perform the successive step of this project. However, that is how to obtain target specificity. One of the routes that we can exploit is the binding of a monoclonal antibody, that is a protein that has a specific selectivity for other protein expressed on cell surface, mainly tumor cell surface. And we perform this conjugation with first activation of the carboxylic group located on the surface of MIL100, and these activated groups have been reacted with the amino group located on the monoclonal antibody to obtain this system. We confirm this binding through HPLC analysis of the solution containing the monoclonal antibody before and after the reaction. We confirm still the nature of the material after the synthesis, albeit a small erosion, a small loss of crystallinity has been observed. And we confirmed as a last experiment the conjugation of the monoclonal antibody through ELISA experiments that take advantage of other monoclonal antibody that are able to catalyze a reaction that we can see. And in this case, this yellow color gives us this information that the bond has been established between the monoclonal antibody and the MOF. So, in conclusion, we synthesized and these two systems. We were able to load high amount of doxorubicin, and in situ encapsulation was useful for to reach this goal. However, we have some ongoing studies. The first is beta analysis, because if doxorubicin has been included inside the system, we should have a reduced superficial surface area. Elemental analysis is fundamental to confirm the real amount of doxorubicin included inside the MOF. Why? Because we have a system containing only carbon, hydrogen, oxygen, and nitrogen. But the only nitrogen that we have inside the system is related to the doxorubicin. So if we determine the nitrogen, the total nitrogen amount inside the system, we are able to we can determine the real amount of doxorubicin inside the system. I would thank you again, the organizing committee for this opportunity. I would thank you for your kind attention.
Okay, thanks, Paolo, for this talk. Now questions, please.
So the doxorubicin probably inside, but it could also be outside. So the elemental analysis wouldn't tell you whether they are inside or outside.
The elemental analysis will give us only information about the amount of doxorubicin, not where
Exactly the location.
But I think that also the
pore is big enough to accommodate.
the pore is big,
Which is
big enough, but the window to exit is not so big. So also the erosion of the material allow the exit of the system.
Do you have, we show video 141 has
Yes.
one crystalline in the middle.
Yeah.
Do you have some SEM showing the single crystals or the amount of them?
That's all right.
You will check.
Yeah, yeah, I will do.
Yeah.
Thank you very much.
Thank you.
Other questions?
Have you tried already the release experiment for the newly prepared?
No, no, we are going, we are doing this experiment to see if there is a change in the kinetic, because if the release will be controlled by the erosion of the system, we should have some differences with the previous system.
And the other thing I was thinking is, so with the monoclonal functionalization, is 100% of the MOFs localizing at the tumor? Because still, since you have degradation, you
Yeah.
could have that circulating.
But the degradation of this system take place only inside the acidic compartment. So after internalization by cells in the lysosomes, the pH is move around 4.5, and in this condition there is the erosion of the
So
system.
it's not dangerous.
No, it should be safe.
Okay, so any other questions? If not, let's thank again. Talk will be given by Mikhail Swetin, talking about